right, we're going to do an example problem that, again, just helps us to utilize this new terminology, electric potential energy, electric potential, potential difference, voltage, reminding us of all the energy relationships, work energy theorem, kinetic energy, and potential energy, and work, and all those things. Again, using this new language in a new way, or the old language in a new way, in the electric world to solve a problem. So, suppose an electron, charged particle, is accelerated from rest through a potential difference of 5,000 volts. So if I put an electron into an electric field, it's going to feel that force. The potential difference gives us an idea of that change in potential that this electron is going to feel. What is the change in electrical potential energy of the electron? What is the kinetic energy of the electron? And what is the speed of the electron? All right, so let's tackle these one at a time. So we want to remind ourselves, of course, that the electron is a charged particle. So the charge on an electron, remember, is 1.6 times 10 to the negative 19th, joules. All right, so let's just kind of remember that. Okay, we want to know the change in potential energy, change in electrical potential energy of this electron. Now we know that the change in potential energy is related to the electric potential. Remember, our electric potential was the electric potential energy per charge, okay? Therefore, our change in electric potential, or our voltage, is equal to our change in potential energy per charge. So you can go back to that video to kind of walk that walk through that if you need to. So if we want to know the change in electric potential, we're given, remember, the voltage, the potential difference, the voltage of 5,000 volts. Okay, so we're given this information. All right, so our change in potential energy is going to be our charge times our voltage, right? And therefore, our charge is minus 1.6 times 10 to the 19th. Our voltage is a positive 5,000. We get a change in potential energy of the particle at minus 8.0 times 10 to the negative 16th joules. So using our understanding of this terminology, potential energy, we're given the electric potential, which is the change in, we're given the potential difference, the voltage, which is the change in electric potential. Change in electric potential is equal to the change in electrical potential energy per charge that is experiencing that change. All right, step one. Step two. What's the kinetic energy of the electron? Okay, this goes back to that work energy theorem and conservation of energy, which tells us that the change in kinetic energy is equal to minus the change in the potential energy. All right? So if our potential energy is minus 8.0 times 10 to the negative 16 joules, then our change in kinetic energy is equal to 8.0 times 10 to the minus 16th joules, a positive 8.0 times 10 to the minus 16th joules. Now this is our change in kinetic energy, not the kinetic energy of the electron after it's been accelerated. So how do we get that? Well, we know that the change in kinetic energy is equal to the final kinetic energy minus the initial kinetic energy. So it's that difference that equals 8.0 times 10 to the minus 16th joules. Now you probably very quickly said, well, wait a second. It said it started from rest. And it does. So our initial kinetic energy is 0. So in this case, the final kinetic energy after this acceleration is in fact 8.0 times 10 to the negative 16 joules. So in this case, what we determined for the change in kinetic energy is in fact the kinetic energy that answers our question, but I just want you to remember that it may not always be the case, right? If that electron was placed into that, between those plates that were producing this electric potential difference, and it's already moving, then this would not be the case, right? We'd still have the same change in electric potential energy. We'd still have the same change in kinetic energy, but the kinetic energy at a given point in time at the end of that motion is not necessarily the same. So, only because it started from rest. So just kind of as a reminder. All right. And then the last piece, what is the speed of the electron at that point in time? Well, that's just our relationship for kinetic energy. We know kinetic energy is 1/2 mv squared. That's our kinetic energy. A little reminder there. And so we have 1/2, and we need the mass of an electron, and the mass of an electron is a known quantity. It's 9.1 times 10 to the minus 13 31 kilograms, super tiny, times b squared. And that's going to equal my kinetic energy of 8 times 10 to the minus 16. Right, so do a little math there, not that complicated math. I solve for v, and I get that the speed is 4.2 times 10 to the 7th meters per second. All right, so again, kind of just re-familiarizing ourselves with the idea of energy, and now using some of this new language, particularly this idea of potential difference or voltage. We're going to really dive into voltages in some future work, and using all that information again just to solve some really fun electric field and electric potential problems. Good job.